to talk about index theory. And I want to start off by defining what an elliptic differential operator is. So that's sort of the first part of the talk. Elliptic differential operators. Operators and the index. I should maybe give a general reference here. So a book that I learned a lot from, that's not particularly easy to digest, is the book by Spin Geometry by Lawson and Michelson. So it's slightly intimidating since it's a thick book, but if you pick and choose parts out of it, you can gain a lot from it. All right, so what are elliptic differential operators? So let's start with sort of the basic case. So the basic case, we just talking about functions on Rn. So I look at smooth functions on Rn, and for my purpose, I want to think of complex valued functions on Rn. So these are maps from Rn into C, which are smooth. And a differential operator here is a linear map from functions to itself. Linear map. Such a linear map is called a differential operator, is a differential operator. And since I'll say the words a lot, I'll just write DO from now on. Differential operator of order K. Well, if it has the following form. So suppose that you have a function f, and you want to apply this map to it. Then this is a new function. This new function should have the following form. You take the old function, you differentiate it a bunch of times in a bunch of directions. So you say differentiated alpha 1 times in the first coordinate direction, alpha 2 times in the second coordinate direction, up to alpha n times into the nth coordinate direction. And then you get a new function here. And then you multiply this by some other function, which will depend on alpha. That's just another smooth function on R. And you sum up for all alpha smaller or equal to k. So here the alpha is a multi-index, alpha 1 up through alpha n, where these things are natural numbers. The sort of value of that is sort of the sum of these things. Okay. So that's sort of the form that the differential operator takes. And to say it's a differential operator of order k, I also want to say, oh, the kth order terms are not all 0. Sort of, and the coefficient here is not identically 0 for some alpha of degree k. Okay. So that's the most basic situation of a differential operator on Rn. Now you can make it more general. By saying, oh, instead of just having complex value functions, we have functions on Rn with values in some complex vector spaces. So let's say E and F are complex vector spaces. Then you look at an operator D from the smooth functions of Rn with values in, say, the complex vector space E into functions on Rn with values in this other complex vector space F. And you want that to be a linear map. And then is a differential operator of degree of order k if, well, if it has this form, but now the understanding, of course, needs to be a little bit different, right? Since if you differentiate this e-valued function a bunch of times, you still get an e-valued function. So that means this thing here needs to turn this e-valued function into a v-valued, into an f-valued function. So in other words, it should be a map from Rn into the homomorphisms from E into F. So if D, if the differential operator, if this operator has form, the form star, with the understanding that now the A alpha, which before was a function with values in C, is now a function with values in the linear maps from E to F. So that if you apply this to an E-valued function, you get an F-valued function. Okay? So that's the differential operator acting on vector-valued functions. Now we're going to globalize it and talk about differential operators on a manifold. So this is the first step in the generalization. And the second step of the generalization, the E and S will be vector bundles, smooth vector bundles over the manifold X.
Mm-hmm. So do I just naively think about it? You have to say what you mean by differentiating a vector value function to begin with. So you have to have some kind of structure on the vector. You just identify the vector space.
Oh, my vector spaces here, I'm thinking of a finite dimensional.
So you just identify Rn and just differentiate.
Yeah, exactly, exactly. So if you have infinite dimensional vector spaces, then the topology matters, but here, nah. So this is of finite dimensions. Okay, so if you have E and F vector bundles, then you can look at sections of X with values in E. And you have a vector space here, which sort of generalizes the space of vector-valued functions on a manifold. And if you have a linear map D from sections of E into sections of F, that is a differential operator of order k. If, well, if it is locally of this form, if D is locally of the form star. Okay, so that means, yeah, you trivialize the your vector bundle. You look at your charts, and then in a little neighborhood at every point, well, a section of a vector bundle is just an e-valued function on a piece of Rn, and similar over here. And then with respect to those local trivializations of your vector bundles and your charts for your manifold, that should have this form here. You could write it a little bit sort of more general. In particular, you could ask, well, what kind of thing is in this A alpha? So now, in this context, the A alpha is just a section of the homomorphism bundle of E into F. Right? So if these happen to be the trivia vector bundle, oh, that's really just a map, smooth map from X into the linear space of linear maps from E into F. Okay, so that's what differential operators are. So let me give you quick examples here. Examples of differential operators. Well, suppose you have a vector field. On a manifold X. What's a vector field? Well, there's the algebraic definition which says, oh, a vector field is just a derivation on the algebra of functions on this manifold. So also known as a map D from the smooth functions of X to itself, which is a derivation. Oh, if you look at it, what it is locally, well, you differentiate in one direction, right? So this is a first order differential operator. So this is a differential operator of order 1. Slightly elaborating on that, you will all know the de Rham operator, right? The de Rham differential. So that is a linear map from the k forms of X into the k plus 1 forms on X. And to recall, k forms on X are sections of a certain vector bundle over X. Namely, you take the cotangent bundle of X and you take its kth exterior power. And then, of course, this one here is also a space of sections, namely of the k plus first exterior power of the cotangent bundle of X. And yeah, this is also a differential operator of order 1.
In both of these examples, they're not complex unless we complexify, right?
Yeah, I'm wavering a little bit on that. So yeah, that works in the complex world. Okay, I'm sorry. Yeah, thanks for reminding me. I should repeat the question. So Mark was asking, oh, but here we're talking about complex vector bundles. So yeah, I need to complexify to make it correct. Or I need to say, oh, everything here works as well with real vector bundles. And it's also only for later purposes. That's word complex. No, absolutely. Okay, now I want to define what it means for an operator to be elliptic. And that is defined in terms of its so-called principal symbol. So definition. So let's say D is a differential operator. Well, let's do it explicitly. So let's say it goes from sections of a vector bundle E to sections of a vector bundle F on a manifold X. There, suppose this is a differential operator of order K. The principal symbol of D is a vector bundle map from the pullback of E into the pullback of F. And I call this sigma of D for principal symbol of D, where the pi is just a projection map from the cotangent bundle of X into X. So what does this do? So I need to describe, well, what's the linear map on each fiber, right? So on each fiber. So this is a vector bundle over the cotangent space. So let's take a point in here. So if I have a point in the cotangent space, total space of the cotangent space, it sits over some point x, right? So let's say xi is a point in the cotangent space over a point x in our manifold x. Then I want a linear map from the fiber of the pullback bundle over xi into the fiber of the pullback bundle over the same point, right? I want a linear map. So this linear map will be, I'll denote that sort of the vector bundle map at the point xi. So what is the fiber of this pullback bundle? Well, that's the fiber over the image of xi under the projection map. Oh, so that's x. So this one here is just the fiber over x of the vector bundle E. And similar, this is the fiber of f over the point x. So now I need to write down this map here. So, okay, what should that be? Well, I already have maps, namely A alpha at the point x, right? That A alpha was a vector bundle map from E into F. So in particular, if I evaluate this vector bundle map at a point x, I get a linear map from the vector space Ex to the vector space Fx, right? So this map will be made from those linear maps. And so I want to write it more precisely. So this will be a big sum of those things. But what's weighted in there is the psi. So I need to explain what do I mean by psi to the alpha, right? What this means is I work locally here. So I'm thinking I'm sitting inside a coordinate chart. If I'm sitting inside a coordinate chart, then this cotangent vector at the point x can be written in terms of the basis, right? The basis of the cotangent space is given by dx 1 up through dx k, up to dxn, sorry. So it will be some linear combination of this thing here. Sum from 1 up to n. Okay? And then this psi to the alpha is defined by saying, oh, this means take psi1 to the power alpha 1 times psi2 to the power alpha 2, blah, 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 times psi n to the power alpha n. So in other words, this is sort of a homogeneous polynomial of degree k sort of on the cotangent space. And so then this one here is a function on the cotangent space with values in the linear maps from Ex into Fx, which is homogeneous of degree k in the cotangent space. Any questions on that? Okay, that's the so-called principal symbol. All right?
So this is, why the cotangent space? I mean, I don't see the role it plays here, because you're just taking a local chart. You could have done a tangent space.
That's true. So the question is, why are we working with the cotangent spaces when we do it, if we work locally anyway, where you don't see the difference much between cotangent and tangent? So the reason is, say, think about a vector field as a first-order differential operator. What would be the symbol? Well, the symbol should be a function on the total space of the cotangent bundle or the tangent bundle. So I'm claiming, hey, if I have a vector field, I see a very natural way, a function on the cotangent space. Namely, at every point in the cotangent space, I have a cotangent vector. Oh, I can evaluate that on the tangent vector that gives me gives the vector field to get a function. So no. So exactly. So this is a natural thing to do. So these things fit together. This local description fits together under transition functions, unlike if you try to do it on the tangent bundle. But later on, we will in fact sort of identify these things when we sort of do topological considerations. So.
I guess like the very pedestrian answer would be that differential operators are made out of partial derivatives. So how do they transform?
Yeah.
Yeah.
Right, that's
Yeah. Okay, great. So that's the definition of a principal symbol. And that's sort of crucial now for defining what we mean by elliptic operators. Definition. So the differential operator of order k is elliptic if, well, now I say it in terms of this vector bundle map. So I have the principal symbol, which is the vector bundle map of the pullback of the domain vector bundle and into the pullback of the range vector bundle. If this one here, and let me say it at the point psi, if this map here is in fact invertible, well, it has a chance of being invertible, since it's a polynomial, homogeneous polynomial of degree k. Of course, it needs to be 0 at psi equal to 0, but we want it to be invertible for any non-zero psi. Is invertible for any non-zero psi. Okay. So notice, in particular, that means, that implies that the dimension of E better be isomorphic to the same as the dimension of F, right? Since this gives us an isomorphism then between the fiber over of E over X and the fiber of F over X. All right. So now an interesting question is, well, what are good examples of elliptic differential operators? So maybe I shouldn't have erased these things here, since we could ask in any of these examples, are these things elliptic? So for example, the de Rham operator, is that elliptic? Well, no, it doesn't have a chance of being elliptic, right? Since it goes from k forms to k plus 1 forms. Well, the bundles involved there don't have the same dimension generically, so no chance, right? According to that remark. So you might say, oh, but what about just a vector field? Is the differential operator given by a vector field, is that elliptic? And the answer is no. I mean, since it differentiates only in one direction, so if you test it on a cotangent vector on which this vector field evaluates to 0, then no, the principal symbol is 0 in that direction. So no, these previous examples are not elliptic. So note previous examples are not elliptic. But you can build an elliptic operator out of the de Rham operator as follows. So you need to do this move here. So you look at, say, k forms and k plus 1 forms. And there's a de Rham operator going this way. Now, if you have a Riemannian metric on X, there's also an operator going the other way, namely the adjoint of it. So now suppose X is a Riemannian manifold. So then you have an adjoint here. This is the adjoint. of d, which is again a first order differential operator. And let me just say what it's characterized by. It's characterized by this adjoint property, so meaning the following. So take d star, you can apply that to a k plus 1 form. Let's say phi is a k plus 1 form. Then the resulting thing is supposed to be a k form. So suppose you give yourself a k form, say psi. Then you can take the inner product of those two elements, of those two k forms. Where this is an inner product that I'm going to describe in a minute on the space of k forms. Sorry, on, yes, k forms of x. And the requirement is that, yeah, you can sort of slide it over in the other slot and make it a d. So that should be equal to the inner product of this k plus 1 form phi with a k plus 1 form that you produce out of psi by applying the de Rham operator. So this is the inner product on k plus 1 forms on x. So how does this inner product work? Maybe do this on the side here. So suppose that you have two k forms, say psi 1, psi 2, or k forms. And k forms are sections of the kth exterior power of the cotangent bundle of x, right? So in particular, if I take a point in x and I evaluate this thing here, this is going to be an element in the kth exterior power of the cotangent space at the point x, right? And similarly, psi 2 will also be an element of that same vector space. Now, you have an inner product on the tangent space. That's going to give you an inner product on the cotangent space, and that gets you an inner product. So it has inner product that I denote might be by these sort of round brackets induced by the Riemannian metric, which gives me an inner product on all tangent spaces. So then I can take these two vectors, take the inner product, so that gives me a number. So in other words, I have a function on the manifold x. And then I can integrate that over x using the volume form. So dvol is a volume form. So then that gives me a number, which is this inner product of psi 1 and psi 2. So in that way, you can define an inner product on all the differential forms, and then you can start talking about the d star. As a side remark, you can also express the adjoint d star in terms of the Hodge star, but that doesn't matter for the context we are interested in here. Okay, so turns out neither of the operators d plus d or d star are elliptic.
So do I need my manifold to be orientable?
No, to talk about the adjoint, you don't need the orientability.
Oh, we're integrating a positive.
Yeah, yeah. I mean, you need to then talk a little bit about, like, what do you mean by volume form? So that would be a form, that would be a density, but
Okay.
that all works out. Okay. So how do we get an elliptic operator? Here's what you do, is you define the so-called Laplace de Rham operator. And I'll need to denote this symbol for it. That's obtained in the following way. You take the operator d plus d star. So you think of that as an operator which goes from all differential forms to all differential forms. Right? Since D produces a k plus 1 form out of a k form, this produces a k minus 1 form out of a k form. But if you add them, you can still view them as an endomorphism of all differential forms. And then you can square this operator. That's the Laplace Theorem operator. And of course, you can sort of multiply it out, right? So you could write it in this form. But then noticing that, hey, this is 0, and hence also the square of the adjoint must be 0, you can also think of it in that way. And if you think of it this way, then you see that, oh, you can really think of that as a map from k forms to k forms. Since the D star makes out of a k form, a k minus 1 form, but then you apply the D again, that produces a k form again, and similar over here. So the Laplace Theorem operator is really an endomorphism of omega k for every k. And so this is an elliptic operator. Okay. Now, what's cool about elliptic operators? Why do we even talk about that? So,
how are you doing sigma d psi as map from fiber from EX to FX? And obviously, just talk about the board that you're about to raise.
so the Laplace. So the question is, why is the Laplace Theorem?
While you're talking about all this, I'll just stare at this part of the board. I'm confused about how this is a map from fiber from EX to FX.
So you're asking about this map here and the definition of this map?
Yeah, so it's like I think it's supposed to be like if you've got like a differential operator on Rn, then like the symbol of it is just supposed to be like a smooth symbol of the Fourier transform.
There's one way of defining it. You can do the pedestrian way. This is a pedestrian way of defining it. And the hard part here is, if you do it the pedestrian way, you need to show that it has the right transformation properties under transition function. But you are happy with the local formula, right?
So what Stephan's saying here is, a pullback bundle, a property of the pullback bundle is that the fiber is the fiber.
Yeah.
So C is an element of the fiber over X. So therefore, the fiber of the pullback bundle is the fiber of the original bundle over X.
So why is this a map from EX to FX then?
Well, because the top and the sorry.
These things are, right? These are linear maps from the fiber to the fiber. So by definition of what we write down.
So why sigma d then? So sigma d is psi.
So now we add a bunch of these multiplied by these numbers here. So then each term here is still a linear map from EX to FX.
Can I say a very pedestrian way of looking at it? So you're writing your differential operator in local coordinates, so you're looking only at the top degree, where parts can contain the top, the highest derivations of highest degree, and then you replace all partial derivatives with just new variable. D over dxi becomes xi I, so that becomes a polynomial from space.
Yeah.
Instead of a differential operator. And
It's not supposed to be a linear map.
it's a linear. It's linear map in a different variable. It's a polynomial mapping size, but it's linear in. So all the coefficients are homomorphisms from E to F. They're just matrices.
Maybe if you wrote the symbol of the Hodge Laplacian,
So you get a
that
polynomial.
would make it more.
Yeah.
C is fixed,
So
so it's not linear in C. But the alphas are linear maps.
Yeah, A alphas for each. So they are matrices, if you will. Like,
So let's do
X to F.
example. So you could ask, well, what is the principal symbol of this Laplace operator? So the principal symbol of the Laplace operator at a point psi. So what kind of thing is that supposed to be? Well, it's supposed to be an endomorphism of the fiber of the vector bundle that the Laplace operator acts on, right? which is the kth exterior power of the cotangent bundle of X. So which endomorphism is that? It's a pretty boring one. It's the identity on this map, on this thing. But then, yeah, that can't be it, since it needs to be a quadratic polynomial of psi. So what's a quadratic polynomial in psi? Well, you take the norm squared of your cotangent vector psi. That's sort of the quadratic polynomial, right? And with values in the endomorphism of this particular vector bundle. So it does depend on psi, but it's also a linear map. For every fixed psi, it's a linear map of this vector space to itself. All right. So let's see. So I was talking about the Laplace Theorem operator. That's an example of an elliptic operator. So, but I now wanted to talk about why do we care about this funny ellipticity condition? How is what?
How do we show that the symbol is just this?
Well, one way to show that this is a true equation would be to write it out in local coordinates, and then you see that this is true. I won't do that. As I said, I mean, this is a survey talk, so I skip totally all details and all proofs, but I just claim a lot of facts that maybe I don't know the proof of myself, but that I read in books. Okay. So here's sort of the main theorem in the subject. It says if D is an elliptic operator on a compact manifold, and I'm always thinking of manifolds without boundary here, then you can look at the kernel of this elliptic operator, and it turns out the dimension of that space is finite. In similar vein, you could look at the co-kernel of this elliptic operator. Turns out that's also a finite dimensional vector space. So that's the major result, and that's why you care about this condition of being elliptic, since that guarantees that you have finite dimensional kernels or co-kernels. So you have numerical invariance that now you can work with. As I said, I won't go into the proof of that. Roughly speaking, suppose that you knew that your operator D is invertible, then obviously kernel and co-kernel will be trivial. Now you don't want to show it's invertible, since you just want to show that these numbers are finite, but you want to show that they're invertible modulo something called modulo compact operators. So that guarantees that kernel and co-kernel are finite dimensional. So you want to show invertibility modulo compact operators. So this is sort of like, you don't want to show that a map has an inverse, but maybe it has an inverse up to homotopy. This is sort of the analyst version of that, right? So now if you compose a differential operator of order k with a differential operator of order L, you get something that differentiate k plus L times, right? So that's a differential operator of order k plus L. Oh, but the identity is sort of a degree, an order 0 operator. So that sort of shows you're out of luck if you're trying to find sort of a pseudo-inverse in the world of differential operators. But there's a larger world of so-called pseudo-differential operators. And the ellipticity condition guarantees that, yeah, you construct inductively sort of something, a pseudo-differential operator, which is a sort of a pseudo-inverse to that original operator, in the sense that the two compositions that you can form are compact operators. So that guarantees the finite dimensionality of kernel and co-kernel.
Is that thing called the parametrics?
It's called a parametrics, is my understanding, yeah. Okay, it's just very, very roughly. Okay, but let me show you that this thing here lines up well with things that we know as topologists. So all of this talk about index theory has sort of a topologist slant to it, since most of the audience members are sort of more topologically affiliated. So let me look at the case of the Laplace Operators operator. So the kernel of the Laplace Operators operator, that's known as the harmonic K-forms. K-forms. So this is by definition the kernel of the Laplace Operators operator from K-forms on X to itself. Now, there's another way of writing the same thing. I mean, you can convince yourself easily that this is the same thing as taking the kernel of the Operators operator from K forms to K plus 1 forms and intersecting it with the kernel with the adjoint, D star, going from K forms to K minus 1 forms. And then you have an obvious map from here into the set of closed K-forms. That's the kernel of this map, divided by the exact N-forms, exact K-forms. Sort of, which just takes a differential form, which is closed, since it lives in here, ignore this condition, and just look at its equivalence class in this quotient. Now, this one here is by definition the Operators cohomology. Okay, Operators cohomology of X. And by Hodge theory, this map here is actually an isomorphism. So there's Hodge theorem. So you can think of Operators cohomology as being isomorphic to harmonic forms. Now we also know that you can have the Operators theorem here, which provides us with an isomorphism of the Operators cohomology and the singular cohomology as coefficients in. Now again, need to say R or C or so. I won't be careful about that. So this is a singular cohomology. And we know from topology that if we assume that X is compact, the singular cohomology will be finite dimensional vector spaces. These are finite dimensional for X compact. And now you see, there's sort of a very different analytic proof of that. Namely, using this theorem, we see that, the harmonic forms are finite dimensional as a kernel of this elliptic differential operator. So it's sort of neat that these things sort of really go hand in hand. The kind of things that we might know as topologists really line up with things that analysts know. Okay. Now, let me note that the vector space of harmonic K-forms, that's a subspace of all K-forms. So note, so the K-forms of X. It's a subspace of all differential K-forms. The note is that this space here actually depends on your Riemannian metric. On the Riemannian metric. Since the operator, the Laplacian, depended on that, and so, and you can see in examples that, no, as you change your metric, the space of harmonic forms really changes. However, its dimension is independent of, but dimension of that thing is independent of the Riemannian metric. So that might lead you to believe that, oh, that is maybe a general story. So whenever you have an elliptic differential operator, that the dimension of the kernel and co-kernel, those are finite by this main theorem, they should not depend on sort of the details. So in particular, as you deform your elliptic differential operator, you might think that, oh, the dimension of these things is independent of that. So this is not true. So note, or maybe a fact, important fact. So if you deform an elliptic differential operator on a compact manifold, then let me call that D. Then the dimension of the kernel of D and the dimension of the co-kernel of D might jump. So no, they can change. Even if you continue to deform it, the dimension does not stay the same. But if you look at the dimension difference, so if you look at the dimension of the kernel minus the dimension of the co-kernel, that quantity, that integer, is actually does not change in your deformation. It does not change. So that's why this is a quantity that has a much more topological feel to it, right? It's independent of these sort of quantitative data, like things like Riemannian metrics. So it's more a qualitative thing, right? So, and if you think of geometry as being sort of quantitative in the sense that they care about volume of their shapes and the curvature of their shape, but you think of topology as qualitative, like as you deform your balloon, its geometry changes, but its topology doesn't, right? So that makes you think, oh, there should be something topological about this index. So this is called the index, this quantity, and this is called the index of this operator D. Now the obvious question is then, well, it has this topological feel to it, so is there a topological way to calculate this index? So is there a topological way? To calculate the index of an elliptic differential operator. Okay. So that is the question that the index theorem addresses. It says, yes, there is a purely topological way to calculate this thing, and it has to do with Thom isomorphisms in cohomology in K-theory. And so that's the next thing that I want to explain. So the next part of my talk will be sort of a first step in this direction. Namely, we'll be looking at the principal symbol, but we want to think of it as a K-theory element. Sort of any questions on this part?
I have one potentially naive question.
Mm-hmm.
If you have an elliptic operator on Rn, can it have an infinite dimensional kernel?
Yes. Yes. So the compactness is essential, sort of the same way as sort of the compactness is sort of interesting to control the topology.
Right.
Laplace, yes.
harmonic functions.
Ah, okay, good. Okay.
Okay. Second part of my talk will be about the principal symbol as a K-theory element. Okay. All right, so let me recall a little bit about K-theory first. So we'll suppose X is a compact space. And let me denote by vect of X the category of vector bundles. Over X. And again, I'm mostly thinking of complex vector bundles, but the whole story would go through with real vector bundles as well. So let me not worry about it at this point. Now, you probably all know how to make K-theory out of vector bundles by saying, oh, you look at isomorphism classes, and that's a monoid with respect to addition, and then you take the group completion of that. Now, I want to write it down in more down-to-earth terms, since at the end, I want to define sort of what is K-theory of X relative A. And for that, it's better to just do it a more sort of down-to-earth-ish. Okay? So K-theory of X, a more down-to-earth description, is defined as follows. You take pairs of vector bundle, say E plus, comma, E minus, where plus and E minus are just vector bundles over X. But you put an interesting equivalence relation on that. This is generated by sort of two moves. I mean, there's an obvious notion of isomorphism between two-such pairs, right? So if you have another pair and these are pairwise isomorphic, then yeah, then you want to declare them to be equivalent. So by isomorphisms of such pairs. Well, but you need to do something else in order to get inverses. And this something else is in the following way. So secretly, when we write these pairs of vector bundles, we really think of it as a difference of E plus minus E minus, right? So in particular, if you think that way, that means if you take a vector bundle and you add it to E plus and you add the same vector bundle to E minus, well, the difference doesn't change, right? And you express that by this equivalence relation. So you say, hey, if you add the same vector bundle F to both things, then you want to declare it to be equivalent to the original thing. So again, this is sort of the part of the equivalence relation that enforces you to say, oh, you really should think of these as differences of vector bundles, right? So the point of doing this one here is that this one here becomes an abelian group. And the addition is given by the direct sum of such pairs. So you add to such pairs by adding each of these components. And the point of this one here is that you want an inverse. And you can show that the inverse to E plus, comma, E minus is E minus, comma, E plus. So you might say, oh, why? I mean, if you add this to that, then you're getting E plus plus E minus, comma, E plus plus E minus, right? But why should that be trivial? Well, by this relation, right? Since that is isomorphic to the bundle. This relation in particular means that any bundle where those two terms are equal is equivalent to 0, right? And that's why E plus E minus, comma, E plus E minus represents 0 in this group. So this one here makes sure that you get an abelian group. Okay, let me do one more thing. Now I want to define relative K theory. So if I have an open subspace of X, I want to define K of X comma A. And that has a similar description here, but it's a little bit more. I have not just two vector bundles, E plus and E minus. I also want to somehow say, I mean, what's the idea of relative cohomology? You want to say, oh, but it's sort of, its restriction to A should be trivial. Well, how do I recognize if such a pair is trivial? Well, if I find an isomorphism between them, right, then that pair is trivial. So somehow I want to have some data that tells me, oh, if you restrict these bundles, E plus and E minus, to A, then they become isomorphic. But in fact, I want to remember the reason they become isomorphic, right? Oh, okay, so I build in the reason in the definition. I'm saying, oh, I want a vector bundle map between there. So this is a vector bundle map. Bundle map. So notice that I didn't say it's a vector bundle isomorphism, just a vector bundle map. But the condition is that if I restrict alpha to A, then it becomes an isomorphism. Is an isomorphism. Right? So that guarantees that if I restrict this thing to the subspace A, oh, then the bundles become isomorphic, so this represents 0 in the K theory of A. And again, I need to take suitable equivalence classes on these things to guarantee that I'm getting an abelian group in this way. So this equivalence relation is generated by, there's an obvious notion of isomorphism between those things, right? Of these triples, meaning it have an isomorphism between the plus parts and the minus parts, but they need to play with the vector bundle maps in between. Then I also want to allow to stabilize. So I'm saying if I have one such thing with alpha, and that's equivalent to the thing that I get by just adding a vector bundle F on both sides, and adding to alpha the identity on F. Right? And one final thing, I want to say, oh, you can homotop the vector bundle map alpha, but keeping the condition that its restriction to A is an isomorphism. So homotopies of alpha, but still restrictions to A doing this homotopy need to remain isomorphisms. Okay.
Why does this agree with the original definition when A is null set?
I don't worry about it. I won't comment on it. I'm sorry. That's a homework problem, let's say.
The third condition is confusing me a bit because like it gives me like 1 and 2, like it gives me like 1 and 2 should be equivalent to this one.
See, the point is like if you have the empty set, there are no conditions on alpha, right? It's an arbitrary thing. No condition of saying it must be an isomorphism on that subset. Well, the space of all vector bundles map is contractible. Well, that's why any two such things are connected by a homotopy. I gave away the solution of the homework problem. Shoot. All right, so let me stop here. And so what we'll do in the second hour, I will show you that, I mean, this thing should already remind you of the principal symbol, right? Principal symbol was a vector bundle map, and it was an isomorphism away from the zero section. So yeah, so you can see that the principal symbol will be representing a K-theory element of something rather, and I'm going to specify that. And then it turns out, oh, the index will only depend on this K-theory class that is represented by the principal symbol. And then you're sort of in business at the topologies. You go like, oh, okay, well, then we just need to construct a map from that K-theory group to Z, which should calculate the index of this thing, right? So that's the idea. So we'll then write down what is that topological index map, and then the index theorem says, oh, the index of the operator is actually the same as what you get by the topological index map.
Should you worry that zero section is not an open set?
Then what?
Should you worry that the zero section is not an open set?
No. This is not final. I will next talk about K-theory with compact support. It's that in that context that will sort of, that the principal symbol will be a K-theory element. All right, thank you.